Professor Tom Wenisch. So in this work, he'll be talking about microsecond level stalls, more commonly known as the killer microsecond. And he'll be telling us about how hardware heterogeneity in the CPU can help address the killer microsecond. Thank you, Dave.
Okay, hello everyone. I'm Amirhossein Mirhosseini from the University of Michigan, and I'm going to talk about our work on enhancing server efficiency in the face of killer microseconds. This work was done in collaboration with my colleague Akshitha Sriraman and our advisor, Professor Thomas Wenisch. So, killer microseconds are frequent microsecond scale pauses in data center applications that arise due to accessing emerging memory and I/O devices, or due to brief idle periods between requests in high throughput microservices. Unfortunately, modern computing systems are not really effective in hiding such microsecond scale periods, as the microarchitectural techniques that we all know about are at best able to hide hundreds of nanoseconds, and operating system context switches are really too coarse-grained for microsecond scale periods. So to battle killer microseconds in this work, we propose Duplexity as a cost-effective, highly multi-threaded server design, which is heterogeneous. It is composed of diodes or pairs of cores that there is a master core in each diode and a lender core. The master core is mainly designed for latency-sensitive applications, and the lender core is mainly designed for latency-insensitive batch applications. The two key ideas in Duplexity are that the master core is able to borrow threads from the lender core in the same diode to fill its utilization holes that arise due to killer microseconds. And the second one is that cores protect their threads' cache states to avoid quality of service violations and excessive tail latency. Altogether, we show that Duplexity is able to improve core utilization by 4.8x in the presence of killer microseconds. So in this talk, I will first talk about the killer microseconds problem in a little more detail, and then talk about why just scaling SMT cores to have more threads is not an option to battle killer microseconds. Then I talk about the Duplexity server architecture, and at the end I will give you some evaluation methodology and results. So, as we all know, modern hardware is pretty good at hiding nanosecond scale stalls, for example, for accessing DRAM, using all the microarchitectural techniques that we have come up with in the past 50 years or so. However, all of these techniques are at best able to hide hundreds of nanoseconds, not more than that. On the other hand, modern operating systems are very good at hiding millisecond scale latencies that arise due to, for example, accessing disks using context switches. But millisecond scale latencies have around 5 to 20 microseconds of overhead. Context switches have around 5 to 20 microseconds of overheads themselves, even if we neglect all the indirect effects such as caching and things like that. However, today's devices and microservices really inflict microsecond scale stalls. First of all, we have lots of new emerging memory and I/O devices that have single digits to tens of microseconds of latency. For example, the non-volatile memory technologies or disaggregated memory systems and so on have single digits of microseconds of latency for loads and store operations. And on the other end of the spectrum, we have high-end flash devices and accelerators that have tens of microseconds of latencies. Also, as we are moving towards microsecond scale microservices, as services are getting shorter and shorter, the idle periods between those services are also getting shorter and shorter. And for example, in a 200 kQps service that is loaded only at 50%, an average idle period is only around 10 microseconds, despite the fact that the system is idle half of the time. So in conclusion, we need hardware and software mechanisms to hide microsecond scale latencies. The obvious solution is multi-threading, but as I said earlier, operating system context switches are too coarse-grained for microsecond scale periods. So one option is to use user-level cooperative multi-threading, but the problem with that is that it requires code instrumentation and recompilation, which is not our focus. Instead, we focus on different variants of hardware simultaneous multi-threading approaches. But the thing to take into account is that we may need to have a lot of, namely more than 10 threads, to fill the utilization holes in the face of microsecond scale stalls and idle periods, as I will show later. So then, just having more and more threads is not really an option, is not really enough, because it adds complexity to the core, namely it complicates the fetch, dispatch, and issue logic of the core, and it requires having a much larger register file, which altogether impose a much lower clock frequency. And also, all the threads basically interfere with each other and put a lot of pressure and crashing in the L1 caches, which ultimately results in a much higher tail latency. For example, our experiments show that tail latency can go up to 5.7x higher due to only a single co-runner thread on an SMT core. And even with a very mild co-runner that has very low IPC, still tail latency can go by up to like 50% higher. So we need to think about this, and basically we need to come up with complexity management and performance isolation mechanisms between the threads to battle killer microseconds. So in this work we propose Duplexity, and in designing Duplexity we have two main objectives. The first one is to maximize performance density and energy efficiency, which are really performance per unit area and performance per watt, because ultimately in cloud systems our goal is to maximize performance per TCO dollar. So what we want to do is to fill all the utilization holes that arise due to these killer microseconds, but at low cost. So our approach for that is to allow cores to borrow threads from each other whenever they face one of these microsecond scale stalls to fill these utilization holes. And the other objective is that we want to minimize disruption and interference between the threads to avoid excessive tail latencies. So our approach for that is to isolate all the stateful microarchitectural structures, including caches, between the threads so that we can avoid quality of service violations. So Duplexity is a heterogeneous server design composed of dyads or pairs of cores. In each dyad, we have a master core, which is mainly designed for latency-sensitive microservices, and it is able to borrow threads from its neighbor lender core in the same dyad whenever it faces these microsecond scale stalls to fill the utilization holes. And the lender core in the same dyad is mainly designed for latency-insensitive batch applications, and the two cores in the dyads share the same backlog of batch threads so that they can use whenever one of their threads faces one of these stalls to remain utilized. So first, let's look at the lender core. As I said earlier, lender core mainly targets latency-insensitive batch applications. Therefore, it doesn't really need out-of-order execution. It can basically get away with only in-order execution. But our goal is to maximize core utilization, and we want to have as many in-order threads that they can saturate the core instruction throughput. And as we observe in this graph, with around 8 threads, we can maximize the instruction throughput, even if those threads are in order. In fact, with 8 threads, it doesn't really matter anymore if the threads are in order or out of order. So we can build a core with much lower cost. However, because our threads are now going to have these microsecond scale stalls, they're not going to be able to run all the time. So if we want to have 8 threads that are really ready to execute, we may need to have more than 8 threads so that we can keep at least 8 of them ready to execute all the time. For example, whenever we have threads that are utilized 90% of the time, having around 10 threads is enough to make sure that 8 of them are ready to execute. However, whenever we have threads that are utilized around 50% of the time, as we see, we may need to have even more than 20 threads to make sure that at least 8 of them are ready to execute at any given point of time. So what we really want to have is to be able to support an arbitrary number of threads, and to do that, we come up with a FIFO run queue of virtual contexts in the memory so that these contexts can swap back and forth whenever one of them stalls. So this is the data path for the lender core we designed, and as you see, the data path is really like an 8-way in-order SMT data path. The only thing that is added to it is that it now has a pointer to basically context queue of virtual context in the memory, and whenever one of the active contexts gets stalled, it gets swapped out and replaced with one of the contexts in the memory. This design is inspired by a prior work called balanced multithreading, and we call it hierarchical simultaneous multithreading. Now let's have a look at the master core. In master core, instead, we are targeting latency-sensitive applications, and therefore we want to maximize single-thread performance. Therefore, we only support a single thread, which we call master thread, and we use all the out-of-order mechanisms to maximize its performance. However, whenever the master thread stalls, we want to borrow threads from the lender core in the same diet and maximize instruction throughput of the core. And as I showed earlier, this figure, we see that having many in-order threads is better than having a single out-of-order thread. So master core, whenever its master thread stalls, it borrows filler threads from the lender core, and all of those filler threads are in-order threads so that they can maximize the instruction throughput of the core. This design is also inspired by a prior work called morph core. So the problem is that when master core stalls and borrows filler threads from the lender core, filler threads may trash all the state in the caches, TLBs, and branch predictors, and therefore when the master thread comes back, it incurs a lot of cold misses and its tail latency would be increased. So the naive solution to this problem is to segregate all the state between the master thread and all the filler threads. Basically, we should have separate caches, TLBs, predictors, and register files for the single master thread and for all the filler threads that can run in the two different modes of the core. However, the problem with this approach is that caches and register files are really large and power hungry, and this approach would basically undermine our objective to maximize performance density and energy efficiency. Therefore, what we decide to do in designing the master core is that we only replicate inexpensive structures, which are the TLBs and branch predictors, and for caches and register files, we do more creative things. For register files, that is that we also keep all the master thread architectural registers inside the register file, even when the master thread is stalled, so that when the master thread comes back, it can immediately continue execution and does not have to fetch those registers from the memory, so that we can facilitate its restart. However, for the caches, we need to do different things, and in fact, the whole reason we come up with the notion of master-lender dyads is the caches. In the regular mode of operation, when the master core is running its single master thread, and the lender core is running eight batch threads, each of them accesses their own L1 caches. However, when the master core stalls and basically it borrows 8 filler threads from the shared backlog, then what we do is that we let the master core access the lender core caches in the same diet, and this has two advantages. The first advantage is that it protects the state of basically the master thread caches, so that when the master thread comes back, it finds small evidence that anything else was running on the core during that period, and its cache state remains intact. It can resume execution with no disruption. And also that all the filler threads access their own cache state from the cache state of the lender core, so that they have higher performance. To address the higher latency and bandwidth requirements of remotely accessing lender core caches from the master core, we provision 2 small 2 kilobyte and 4 kilobyte L0 caches on the path from the master core to the lender core L1 caches, so that they can basically perform as small bandwidth filters and alleviate the bandwidth pressure problem. We also use these L0 caches as spilling buffers, so that whenever we want to evict the filler threads from the master core, we can use them to make the master thread continue almost immediately as its stall resolves and when it comes back, so that it experiences minimal performance overhead. So to evaluate Duplexity, for the master thread we use open source microsecond scale microservices, and for the filler threads we use data parallel distributed graph algorithms. We compare Duplexity against various baselines, including single-threaded out-of-order based design, an SMT-based design, and a variant of Duplexity where we replicate all the stateful structures, including caches and register files, which we talked about that is not a good idea, and we want to see why in our evaluations. There are also more alternatives in the paper that I will not talk about in this talk. First, let's look at issue bandwidth utilization of the core. As we see, Duplexity is able to improve core utilization by 34% with respect to an SMT-based design, and its utilization is only within 4% of the utilization achieved by a design that replicates everything, including caches and register files. However, when we look at performance density, which is performance per unit area, which also takes into account the area of each design, we see that Duplexity is better than everyone else, and namely it improves performance density by 49%, 28%, and 10% compared to the baseline SMT and even the design where we replicate everything. Because that design has a lot of area and it's not an efficient design. We observed similar trends when we look at performance per watt results, but I'm not going to show that for the sake of time in this talk. And finally, when we look at tail latency, we see that a naive SMT-based design that co-locates to any two threads is not really a good idea because it worsens tail latency by 2.7x on average, and in fact the tail latency can go up to 5.7x. However, Duplexity manages to maintain tail latency only within 19% of a baseline that does not perform any collocation, and while it's able to improve throughput by a much higher degree. So, in conclusion, killer microseconds are frequent microsecond scale pauses in data center applications, but modern computing systems are not really effective in hiding such microsecond scale periods. We propose Duplexity as a cost-effective, highly multi-threaded server architecture which is heterogeneous. It has master cores, which are mainly for latency-sensitive applications, and lender cores that are for latency-insensitive batch applications. And master cores are able to borrow threads from the lender cores in their own diet to fill all the utilization holes that arise due to killer microseconds. And also, they're able to protect their master threads cache state so that they can avoid quality of service violations. Altogether,